Okay, we're ready to look at the technique of integration by partial fraction decomposition. And this technique we use on rational functions. So we need a little bit of a toolkit first. And so let me give us a couple of definitions to remember. So our rational function, we'll call it r of x, is a function that is a quotient of polynomials. Okay, so the numerator and the denominator are polynomials, and that is what makes it a rational function. And note, polynomials, the domain is all real numbers for each polynomial, but a rational function has the added feature of having a polynomial in the denominator, so the domain of all rational functions is the set of all x such that q of x is not 0. Okay? All right, so let's look at a couple of examples just to make sure we're all on the same page. That's a polynomial of degree 2 on top, of degree 1 on bottom. That's a rational function. I could have the degree bigger on the bottom. That's a rational function, a quotient of polynomials. That's actually a rational function. So this is a 0-degree polynomial over a first-degree polynomial. And every polynomial itself can be written as itself over 1, which is a rational function as well, because it's the polynomial over a 0-degree polynomial. So remember that our polynomials can't have any negative exponents, fractional exponents. We don't have any roots, so that's what a rational function is. Okay, we're going to say a rational function, for our purposes here, is in proper form if the degree on the top, so I'll say degree of p of x, because based on that's our top, q of x is our bottom. So if the degree on the top is strictly less than the degree on the bottom, then we will say that our rational function is in proper form. Okay, if it's not in proper form, we are going to do some long division to get it in proper form. So we will apply long division, polynomial long division, which we might need to remember also. Okay, so let's look at an example to help us remember how to do polynomial long division. So let's say we have the following. R of x is equal to x plus 1 over x plus 5. That is a rational function, a polynomial over a polynomial. The degree on the top is 1 and the degree on the bottom is 1. That means that the degree on the top is not strictly smaller than the degree on the bottom. So this is not in proper form. Okay, so we are going to apply long division. And remember how we do that. So we will take this, the denominator, and we will divide it into the numerator. And we do it in a very similar way that we do long division of just, let's come over here and look at numbers, right? So if I want to figure out how many times 13 goes into 54, I ask myself, like, what's the largest number I can multiply to 13 to give me a number that is less than or equal to 54. And so we would say 4 here, we would get 52, and 2 would be our remainder, right? Okay, so here we do a similar thing. We ask ourselves, what do I need to multiply to x to give me that x? And that's just 1. So then we re-multiply, like we did over here with the 13 and the 54. And we get x plus 5. And then just like here, we subtract what we just multiplied from the x plus 1. So the x's should cancel, and we should be left with 1 minus 5 or minus 4. Okay, now that is our remainder right here. Just like 2 was our remainder over here. But what can we do with that? Well, what this really translates to is 54 divided by 13 is equal to 4 plus the remainder over the divisor, right? So what this then translates to is x plus 1 over x plus 5 is equal to 1 plus the remainder over the divisor. So very similar. Okay, so that's how we will apply long division. Let's see why that might come in handy when we're looking at an integral of a rational function. Okay, so we have x cubed plus 1 over x minus 1 dx. And we always run through all of our techniques that we already learned. Do I see an easy simplification? Do I see an easy u sub? It's not one of my trigs integrals. I don't see this as an inverse trig sub. This is a rational function, so I'm going to start thinking about the things that we talk about today. But when we apply partial fraction decomposition, we need it to be in proper form, and it's not. So we're going to first get this into proper form. That is, the degree on the top is not smaller than the degree on the bottom, so we're going to do long division. So we're going to take x minus 1, and we're going to divide it into x cubed plus 1. We ask ourselves, how many times does x go into x cubed, or what do I multiply to x to give me x cubed? That is x squared. We then remultiply x cubed minus x squared. This is something I meant to tell you also. So because we want to subtract our like terms, what we do, let me erase this, when we have, when we're missing some of our powers along, with our descending powers from our highest degree, we insert zeros here. And we do that so that it just holds markers for us. All right, so now if I remultiply the x squared and I line things up, I get x cubed minus x squared. I'm still going to subtract off that expression, which means those terms should cancel by design. So x squared minus a minus x squared becomes just x squared. Okay? So that becomes x squared, and then we can bring down the plus 0x, and we do this again. What do I multiply to x to give me x squared? And you would say a plus x. I remultiply and line up, so then I get x squared minus x. I'm going to take that expression and subtract it. The x squared should cancel, and I should now have x minus a minus x, or an x. Lastly, we're going to bring down that 1. And we do it again. What do I multiply to x to give me x? You should say 1. Remultiply. Line them up and subtract. The x's should cancel. 1 minus a minus 1 is a 2. Okay, so let's come over here. Well, I'll come down here. This expression becomes the integral of x squared plus x plus 1. Plus the remainder over the divisor. And now we can tackle this, right? This is just a power rule, power rule, power rule, and a logarithm integral, right? So just to finish this problem up, this should be x cubed over 3 plus x squared over 2 plus x plus 2 times the natural log of x minus 1 plus c. All right, so that's going to be our toolkit, and in the next video, we'll start looking at the different cases where we actually apply partial fraction decomposition.